Alrighty, you guys. So here's a video for lesson 1-2 of BC Calculus in case you missed it. I know a lot of you guys were out for the ASB trip, so hopefully this will help you catch up to speed. Just warm up, we just practiced our unit circle. Just write in a unit circle, give it a go, and then we're going to do some more practice later on in the week. All right, we got a last things from Friday that we didn't quite get to. So on Friday, we were talking about just getting into limits. And our first approach for limits is always direct substitution, right? Just plugging in the number. If we plug in our number and it spits out another number, we're golden. That's the answer. If we plug in our number and it spits out a number divided by 0, that means it does not exist, and we're all done there too. We'll talk about the determinant form later on when you get 0 over 0. So for 23, if we just plug in our x approaching 3, that's going to give us 29. And since 29 is just a number, that's all we got to do. We're done. All right. Now, 24 looks a little scary because we have a denominator, so that should make us a little nervous. But we're just going to plug and chug and see what happens. So that gives us 1 squared plus 1, 1 plus 1, 2 over 2, or in other words, 1. All right, also golden. Another example where direct substitution works. Finally, we have our trig example. We're going to plug this in. That gives us cosine of 2 pi over 3. All right, when we look at our unit circle, that spits out -1/2. Another lovely number, and we're all done. So those are our kind of intro to limits with just direct substitution. We'll get into trickier ones later. Though before we move on some of this limits, we're going to talk about piecewise. Now, I had a couple questions about homework problems that were on piecewise from Friday, so we'll talk about those too. To start with piecewise, what we're really asking, like every limit, we're asking, does our left-hand side equal our right-hand side? Right? If they're equal, then we have a limit. Okay, if they're not equal, then we don't have a limit. So we're going to tackle these. Our first one here says, as x approaches 1. Notice that's our breaking point, right? This side is our left side, our less than side, and this side is our right side because it's our greater than side. So we're always going to have generally the same approach for these. We're going to first plug in to both sides of the break, right? The left-hand side and the right-hand side. And second, we're going to ask, are they equal? And those are really our two steps. So first, let's plug it into the left-hand side. That's going to give us 4 minus 1 equals 3. And plug into our right-hand side. That's 4 times 1 minus 1 squared. Also gives us 3. So since these two are equal, we get the limit as x approaches 1 of fx equals 3. And we're all done. Okay, so there's one piecewise example. 27, we're going to do the same approach. Again, we're looking right here at the break, right? This is our less than side. There's our left. And this is our greater than. That's our right-hand side. So we're going to go ahead and plug 1 into both the left and the right. So the left would give us 3 times 1 minus 1 cubed, which is 2. And our right-hand side would give us 2 times 1 minus 1, which gives us 1. All right, so we should be able to see that these are not equivalent. The left is not going to the same place as the right. So we get our limit as x approaches 1 of g of x does not exist. All right. All right, now if we're looking at the same piecewise function up here, but this time we're going to be taking the limit as x approaches -1. So this one's really asking which bound are we looking in? So -1 is in fact less than 1. So we're looking in the top. -1 is definitely not greater than 1. So we don't even have to worry about that second problem. We're just looking in that left domain. And this is just a plug and chug. Okay, so we're going to say 3 times -1 minus -1 cubed. That's -3, and that's going to give us +1, gives us -2. So our limit as we approach -1 is -2. And we're all done for that problem. All right, so let's look at that last night's homework problems. I had a couple questions on number 16 and 17. Now that we did the notes for piecewise, we should be good to go, but let's just do them together really quick. If you already did these, you can go ahead and skip ahead. Good for you. And let's see, for 16, we're looking at this large piecewise function that's given to us. Now, one difference between this one and our last example is that it actually has 2 breaks in the graph, right? Right here, we're breaking at x equals 0. And right here, we have a break in the graph at x equals 2. All right, so number 16 is asking us as x approaches 2. So we want to look at these two equations. This is our less than side, that's our left-hand side, and this is our right-hand side. And we're going to go through that same process. We're going to plug 2 into our left-hand side and our right-hand side and see if they match up. So the left-hand side would give us -2 minus 3. And our right-hand side would give us 3 times 2, 6. All right, so since our left hand and our right hand side do not match, we get our general limit as x approaches 2 does not exist. All right. So moving on here for 17, the good news is we're looking at the same piecewise function. We've actually done all the work already for this one. This is the limit as x approaches 2 from the left, right, that less than side. So from the left-hand side, we already did that. Bring that on over, and we can just say that this must equal -5. There's your left-hand side limit. Moving on here, I'm not going to make a big deal out of this one. It's just a kind of a rarer function I wanted to make sure we've all seen. So they're called greatest integer or ceiling and floor functions. This one's called a floor function because it's got these little nubs that look like a floor. If we had them up on top, it would be called a ceiling function. Okay, the way these work, it's just a different way to round. So generally the way we round is we use midpoint rounding, which means if you're at 3.5, we round it to 4, right? But if I was at 3.49, I'd round it down to 3. That's called midpoint rounding. We do it all the time. This is just a different type of rounding. So when we're talking about floor functions, it takes any decimal and brings it down to the nearest whole number. So in this case scenario, 3.5 would just go back down to 3. 3.2 would just go back to 3. 3.99 would just go back down to 3. It's not till we get, 4.01 that we go to 4. So that's how those floor functions work. And as far as our limits, they're just normal graphical limits. I know these ones can look a little scary, but it's the same process. So for instance, if I'm looking at x equals 1/2, that would be right here. I actually have a filled in point there. I have a solid line that is 0. And that's it for my graphical points. If I go to x equals 1, that means I'm looking right here. Now I have a big jump on this one, so that's a does not exist. Right? There's a jump function going on. And then if this one is a different function, we'll worry about this one later. All right, you guys, we're going to move on to our second lesson on page 6 to 8. Going to continue our pre-calculus A review here. All right, we're going to start talking about how we approach limits analytically. So we've already talked about direct substitution. That should always be our first step when we do a limit. When you do direct substitution, one of 3 things will happen every time. Okay? Either you'll get a number divided by 0. Okay, so like 2 divided by 0. And we know we can never ever divide by 0. That's when we get does not exist, right? Or in other words, we have an asymptote there. The other one that we always hope for is that we just get a number, right? Something like 2. That means that's our answer. That's our favorite. And then the most difficult, if you plug it in, we get 0 over 0. That means we are not done yet. 0 over 0 means that we have a hole in the graph, or in other words, a removable discontinuity. All right, which means we have more work to go. If you get the indeterminate form, so if that's 0 over 0, these are our steps. Yeah, I would say most of the time we're going to approach by factoring. Usually we can factor it, cancel out the factor that's the problem, and then re-plug it in. If that doesn't work out, we're going to have to do conjugates. That's when we build multipliers and then multiply them out. And then our least common, but sometimes comes up, is trig identities to simplify out things with trig in it. All right. So I'm going to do what I preach for this first problem, right? You always should plug it in and make sure what form we're in. So if we plug in our 0 here, we'd get 0 over 0, 0 plus 1, which is 0 over 0. Okay, so this tells us that we probably have some factoring to do. Now, luckily, number 1's already been pre-factored for us, so we should be able to see our x cancel out. And we're left with the limit as x approaches 0, 1 over x plus 1. All right, now we get to re-plug in. Try again. All right, and this time it does work out. We get 1 over 1 or just 1. And that is our answer. All right, let's look at 2. So 2, you guys, if we plug in 2, it's going to give us 0 over 0. So we know we got to get into some factoring. Hopefully, you guys, we can see that we have a difference of 2 squareds right here, right? We could rewrite this as x squared minus 2 squared. So we know we can factor that as x minus 2, x plus 2, right? Our a minus our b times our a plus our b. When I rewrite that out here, we should see that our 2 factors here can cancel out. Once we've canceled out, we want to try again. We want to re-plug in. And there you go. This time we got a number and we're good to go. All right, you guys, our last one here also will give us 0 over 0 when we plug in. And when we're looking to factor, we're looking right here. Now, we're all usually pretty solid on our difference of 2 cubes, but we might not be so solid on our difference of 2 cubes here. We'll have x cubed minus 1 cubed. All right, if it's been a while since you factored cubics, this is a kind of common one to put on the test more than any other cubic because it's a little simpler to factor if you know the trick. So just like the difference of 2 squares, we kind of have a formula that we can use every time. And it starts off with our x minus 1. All right, and then we get our just regular binomial here of x squared plus x plus 1. So that's what this top part is going to factor into. This is definitely a helpful thing, so if you want to highlight it, remember that one. All right, and our 2 factors cancel out, and we're left with just the limit as x approaches 1 of x squared plus x plus 1. And there you go. We got our lovely little number. There's our answer. The limit as x approaches 1 is 3. All right, so 4, we get to this kind of dreaded conjugate, but I'm going to say don't fear the conjugates. They're not too bad once we've had a lot of practice with them. So first thing we got to see is when you plug it in, we do in fact get 0 over 0. So we're in that indeterminate form again. It also doesn't look too good for factoring unless you like factoring with radicals, then go for it. So what we're left with is building a conjugate. And we kind of have steps for conjugates. First, we ask, what is the scary part? Is it the numerator or the denominator? And definitely our numerator is the scary part. So we're going to duplicate that. The only thing we're going to change is the sign right there in the middle. And that builds a conjugate, right? We have the same terms, we just flip the sign. And then we have one of our commandments of math. Whatever we do to the top, thou must also do to the bottom. There you go. And we've built ourselves a lovely conjugate. Yay. All right, now we do some multiplying out. What we've done is we've built ourselves a difference of two squareds again. We have an a minus b times an a plus a b. So just a reminder, a minus b times a plus b equals a squared minus b squared, our lovely difference of two squareds. When we multiply out this top, we're going to get the square root of x squared minus 1 squared, or in other words, x minus 1 on top. Okay, now on the bottom, we want to leave it alone. Leave the bottom alone. So this is the most common mistake people make. They get all this way, and then they see, oh, I really should multiply this out. Fight the urge. It makes everything a mess, okay? So keep the bottom factored out. And the reason you want to do that is it allows us to cancel out these two factors. And then we're left with the limit as x approaches 1 over 1 square root of x plus 1. We're going to plug it in and see if it works. Perfect. We got a number. We're good to go. So it's a super quick review of conjugates. All right, let's look at this one. This is a limit from the right. Now, there's a couple different ways to do this. We're going to do just kind of a checking a number. Now, remember, when I say 2 from the right, I really mean a little more than 2. 2. All right, so let's check a couple points. So if I'm saying, hey, if I start at 2, what's a number a little bit more than 2? Something like 2.01, right? That's really close, just a little bit more. And something even closer would be like 2.001. Let's switch these positions. 2.0001 is even closer. All right, so what we're going to do is we're going to check. We're going to see what is this value and what is this value. So if I plug in 2.01, I'm going to get 2.01, 2.01 minus 2. All right, and when we do that, we end up with 201. All right, so at that point, I'm seeing that it's a large number, but not quite sure what's happening. So I'm going to go ahead and check this one right here. 2.0001, 2.0001 minus 2. Okay, great. Now when we plug that into our calculator, we're going to get 20,001. So 20,001. All right, now when we're talking about these left and rights, what we're talking about on the graph at x equals 2, we have this asymptote going on right here. Right, when I plug it in just regular 2, that would have given me 2 over 2 minus 2, which is 2 over 0. That means we have an asymptote right there. Okay, and this time we're looking from the right-hand side. So my question is, are we going up towards infinity or down to negative infinity? And looking at these numbers, it definitely seems to me that we're increasing, so we're going to infinity. All right, so our final answer here after all that work is we say the limit as x approaches 2 from the right of our function, approaching infinity. Okay, you guys, quick comment about limits before we move on here. I love to spend more time on factoring and conjugating the lefts and rights of limits, but unfortunately in BC, we have a lot to cover and not enough time. So if you're still struggling with these things, that's totally okay. Please just come see me. I'm here after school anytime, and I'll happily review some of the stuff with you. It's really important that we have our foundations down really strong before we move on to the more complicated stuff. Talk about continuity with that piecewise function. So again, we did some of this stuff on the homework, but we're asking about something to be continuous. That means there is no holes and no jumps and no asymptotes. Okay, so that's kind of what we're checking for. First, let's start with this bottom row. So this is saying if x is 3, then y is 5. That's just giving us a coordinate point. We have 3, 5. We can start with that. 1, 2, 3, 4, 5. There you go. All right, now let's get into this top part. Now, if I were to plug in 3 into this equation, all right, we're going to end up getting 0 over 0. Whenever we see 0 over 0, that means we need to factor. So we're going to go ahead and factor out this top part. We can factor it as x minus 3 times x plus 1. And then our x minus 3 can cancel out. So now we're going to re-plug in with our leftover here. That's going to give us 3 plus 1 equals 4, which means we have an open point at 3, 4. An open point. And now we're not quite sure what's going on in the rest of our equations, doing some squiggly, some direction. But this information right here is enough to tell us that it is not continuous. Even more than that, we can say what type of discontinuity it is. Since it's a hole, we know it is a removable discontinuity. Okay, that's what 6 is asking us to do. All right, 7 is a similar problem, but this time it's telling us to assume that it is continuous at x equals 2. So what we're going to do is we're going to start by plugging in x equals 2, right? That's where this break could occur, is at x equals 2. Then we're going to set the two equations equal to each other. Right? And we know we can set them equal to each other because it's given that they are continuous. They are equal. And then we're going to solve for a. All right, so what this looks like in action, that would give me 3 times 2 squared plus a. Let's plug it into that side. That's going to be equal to 2 minus 3. So that's going to give us 12 plus a equals -1. We're going to go ahead and solve for a. We have found what the problem's asking. So what this means is if a equals -13, then g of x is continuous. If a is literally any other number other than -13, then g of x is not continuous. All right, you guys, that is a very common problem. They like to kind of embed that one, especially in free responses. All right, you guys, we have some more limit calculations. Notice that these are kind of big ones. We've got a bunch of cubics here, but we're always going to start with the same approach of direct substitution. So when we directly substitute 1 in for this top, we're actually going to end up with 1, and the bottom is going to give us 0. Even though this might look like a really, really scary problem, it's not. Just by dividing a number by 0, we know the answer does not exist. And that's it. We're done. We don't have to do any more work for A. Now B is a little bit more work. It takes some factoring with cubics. So when we factor out this first one key hint is it's a lot easier to factor cubics if you kind of know what factor you're trying to take out. So I already know when I plug in 2, I'll save you some work here. We're going to get 0, 0. Okay, it's going to be in the indeterminate form. And the problem that's occurring is that we have an x minus 2 in the top times some stuff, and we have an x minus 2 in the bottom multiplied by some stuff. We just got to do some factoring to find these. Okay, so when we factor out that big cubic, it actually ends up being the limit as x approaches 2 of x minus 2 times x squared minus x minus 1, x minus 2 times x squared minus 1. Now that we factor those out, we can cancel them out and re-plug in. All right, in this top here, we get 4 minus 3, so there's 1. And in the bottom, we're going to end up with 3. So 1/3 or, 0.333, whatever floats your boat. Okay, now we get to review the intermediate value theorem. I love the intermediate value theorem. Pretty much says if you have a f of c between our f of a and our f of b, so some number between here, then we must have a c between a and b. Okay, we have some steps we can follow every time here for our IVT. Step number 1 is we actually have to find the values of f of a and f of b. Okay, step number 2, we have to actually check f of c is between f of a and f of b. All right, and our third step is to check that the function is continuous on the interval a to b. Okay, it's tempting to forget this step, but it's really important. So if all of this applies, then we can say, therefore, IVT applies. And then we can say there exists some C between A and B. Now remember, this is a formal proof, so you need to actually have that full sentence at the bottom. It doesn't have to say it exactly in that way, but we would need to refer back to IVT and then say that there exists some value C in the interval A to B. So let's give that a go. Whew. Okay, first one. Our first step is to find f of A and f of B. Now keep in mind, the beginning of our interval is A and the end of our interval is B. So if I'm finding f of A, or in other words, f of 0, plug that in. Just going to spit out 0. F of B is f of 5. So that'll get us 5 squared minus 5. In other words, 25 minus 5 is 20. Okay, so we have kind of our start and our end. Now we have to just verify that f of c, or 12, is between these, right? 12 is between. Okay, we're doing good. Now our third step is to make sure that f of x is continuous on the interval. Now, if we're looking at this, to check for continuousness, we're kind of asking, is there anything in the denominator that could make it not continuous, or is there anything under a radical that could make it not continuous? None of those things are true. That's a function that's always continuous. So we know f of x is continuous. So we're good to go. So then we can say therefore, or my lazy mathematician way of writing it is these 3 dots. That's just a way to say therefore. Okay, therefore, IVT applies. And there exists a C in the interval 0, 5. It's a perfectly fine way to write it. Okay. All right, now for B, we could do the same approach. We could plug in our new A and our new B, check to make sure G is between it. And then we get on to our third step. Our third step is to check that G of x is continuous. We're going to save ourselves a little time by starting by that step. So looking at G of x, we should be worried because we have something in the denominator that can make it not continuous. So if I were to plug in x equals 2 into here, I would end up getting a 0 in the denominator. So therefore, G of x is not continuous at x equals 2. Now, since x equals 2 is in fact between 0 and 3, that means G of x, that means G of x is not continuous on the given interval 0 to 3. We can say, therefore, IVT does not apply. All right, which essentially means we can't guarantee there's actually a C value between those numbers. We get there, we can move on. All right, let's look at 10. 10 is a little different. It's referring back to our 9a example over here. And our 9a example is going to ask us to find the actual value of this c. Right, we said it exists, now what is it? And the way we're going to do this, whenever it asks for the exact value of c, we're going to say f of x equals f of c. And we plug it in and just solve for the value of c. So f of x is x squared minus x. F of c, they told us right here, is 12. Now this is solving a quadratic, so we want to go back to our Algebra 2 days. We're going to move that 12 on over, get it all set equal to 0, and then factor. So this is x squared minus x minus 12. Factor it up. And then solve each of these factors. So we get our terms x equals 4 and x equals negative 3. Now we're almost done here. The one thing we have to consider is that it can only be one of these, right? Which c value is going to work? And to figure that out, we look back at our interval over here. Our interval told us that it had to be between 0 and 5. So x equals negative 3 is not between our interval 0 to 5. So it's not an answer. It's got to be x equals 4. Okay, guys. Again, in the name of time, we don't have enough time to go back over everything from pre-calculus, but I did want to mention these are our most common graphs, right? These are our parent graphs. It's one of the things we assume you guys are already familiar with. So if you're feeling a little rusty with your parent graphs, please make sure you re-familiarize yourself with them. There won't ever be a question on the AP test where it'll say, like, here's a graph, what's its function? There won't ever be anything that's simple. But it is very helpful to kind of be able to identify what kind of function they're asking about. Can help us get along. Especially here in calculus, and it's really important to tell the difference between sine and cosine, right? Keep in mind sine starts in the middle, cosine starts on the top. So those are particularly helpful. I wanted to brush up your memory on graphing adjustments, right? Especially on our reflections, how putting a negative on the outside of the function versus as an input on the function can switch how we reflect it across the x and the y, and how we do shifts is adding it to the outside, shifting left and right is adding to the inside, and so on. So again, I won't be testing you on this. It won't be on our unit test, but it's really a good thing to brush up on. Okay, guys, that should catch you up to par here. We're going to go ahead on ahead. Now we should be all ready to do assignment 1-2. Okay, guys, assignment 1-2 is due in class tomorrow. Please bring any questions that you have from it. First thing, we'll start off there. Okay, guys, I hope you have a great evening. I'll see you all tomorrow.